Hi everyone, it's Vicky here, and in this tutorial we're looking into flip fluid simulations with particular attention to two shelf tools, Flip Fluid from Object and Emit Particle Fluid. I split the tutorial into three parts to make the navigation easier. Part 1 explains what flip fluids are and how the networks work. Part 2 looks into setting up colliders, including static, animated, and deforming objects. Part 3 shows how to add additional forces to the simulation, such as pop wind or pop velocity. Before starting this tutorial, I'd recommend watching my other videos on how to set up your scene for simulations and understanding liquids for dynamic simulations. They will give you further understanding of the topic and also make this tutorial much easier for you. But without further ado, let's start. Please keep in mind that I'm using the technical desktop and I've already prepared my scene for the simulation, so I'm ready to start. But before we create anything, let's have a look at the shelf tools that we have here in Houdini. So the first tab is called Particle Fluids, and we can find a lot of useful shelf tools here. They are all basic flip fluid simulations, plus some tools for adding parameters, forces, and effects such as viscosity, suction force, or white water. Today we'll be looking at Flip Fluid from Object and Emit Particle Fluid. The second tab is called Viscous Fluids, and this is very similar to the previous one, with the only difference that these shelf tools give us some additional parameters. So some parameters are already set up for us, such as, for example, temperature for lava from objects. So you could use these tools and then add parameters yourself and switch them on, but instead of doing that, you can just use these shelf tools, which are already set up. And the third tab is Oceans, but part of these are not flip fluid simulations. Some of these are just deforming planes that can be used to fake large oceans or large surfaces with liquids. It's far more efficient, and also it's a clever way of faking huge oceans and only simulating a small part of the scene. We also have colliders, of course, that we will use today to add collisions to our flip fluid simulations. The tool we're going to use first is the Flip Fluid from Object, and when you hover over, you will see that it creates a flip fluid object from subgeometry, which means we need a subgeometry first, so surface operator, and it's nothing else than just a simple geometry. So let's create it. Let's go to the tab menu, type geometry, okay, and let's zoom in. We name this one to Pick Geo. I will now dive in, and in here, you might have guessed, I want to create a pick head. Okay, so test geometry, pick head. Let's drop down this node. And as you can see, pick head is quite detailed, but for simulations, we do not need that much detail. So what I will do is change the difficulty to easy, and this will get rid of the shader and also reduce the detail on the geometry itself. All right, so now I want to create a transform node. Let's display it, select it, and I will zoom out because I want to move the pick head up. So you can switch on show handles, and now you'll be able to do that manually in the viewport, or you can use these values. So for example, type 6 in here to move the pick head up. All right, let's drop down the last node in our network. This will be null. Make sure to display it, and we'll rename this one to out pick. Okay, so now we have our three nodes: the pick head, the transform node, and the out null, which is displayed. Let's go back to the object level now, and we're going to use this node, this shelf tool, for the very first time. So what I want to do is click on the gray background to deselect everything. I do not want to have anything selected in my network. Now I'll click on the Flip Fluid from Object, and it will give me some tips on what I should do next. So it says select object to convert into a flip fluid. So this will be our pick head. I select in the viewport and press enter to accept selection. So I press enter with my cursor still in the viewport. After a while, you will see that the pick head disappeared, and now we have a lot of dots here, which are the particles. So it's similar to the representation of liquids in physics. So you can see here that the tool turned our geometry into a cluster of particles. So it is mainly a particle simulation with some aspects of grid volumetric solver. So we can use these two aspects to combine both particles, so for example fluid, liquids, and volumes, so for example white water, which you can use for foam or splashes. Let's go to the object level now, and let's have a look at the nodes we have, the new nodes that we have here. I will press H to home all to see all the networks. Okay, and let's place them in order. So the first one is PIC-Geo. So this is our source. This is the PIC geometry created, and you can see that it's hidden, so we can display it if we want to see it, but we want to see the particles, so this one is not displayed. Then we have Particle Fluid Interior. Okay, so this is our PIC-Geo fluid interior. Let's dive inside, and you will see that nothing important really is happening here for us. There's nothing we can change, so we just have a simple object merge node, and you can see it merges PIC-Geo fluid render with this merge node. So we're not going to change anything here yet. Let's go back to the object level, and we can even hide it if we want to. Okay, the next node is the green one, which is called AutoDopNetwork, so the dynamic operator network. Let's dive inside, and you'll see that in here we have a lot of nodes, new nodes, and everything that we do with the simulation, so whether it's adding forces of adjusting colliders, we'll do most likely in here. So let's go from the top. The first thing we have here is called flip object. And let me just scroll up to see the options. So in here we can change the quality of our liquid. So we have the first thing called particle separation, and the particle separation is the distance between the particles. And if I increase that distance, you will see that we will fit less particles inside the geometry. If I decrease that distance, you will be able to see that we have a lot of particles. So we managed to put more particles inside the PIC head geometry, which means we also have more detail. So you need to adjust this value for your simulation. For tests, we usually use quite high values, so maybe 0.07. So this is low enough, so high quality enough to see what's happening with the liquid, but then it will not take ages to simulate. Okay? And then once you have your simulation ready, you can decrease that value to increase the quality and cache it and render it out. The next thing we have here is the grid scale. And as I already mentioned, flip simulation consists of two, so particles and grid solver. So you can see it here that we have the particle separation and the grid scale. And the grid scale is multiplied by particle separation to determine the final quality of our simulation. And the best way to visualize that is to scroll down, go to guides, okay, then switch on collision, switch off particles. Okay, I'll just zoom out. And now when I play it, you'll see this huge box here, okay? So what we want to do is visualize it as grid. So let's go to the tab called collision over here and switch on use plane. And now when I play the simulation, you will see that we have this plane with that number of boxes, and this is our quality, also the quality of the simulation. So now if I scroll up and change the grid scale to 1, okay, now I need to go back to the very beginning and play it again. Now you will see that we have higher number of boxes, so it's higher quality. So sometimes for colliders, you'll see it later, we'll have to adjust the grid scale and the particle separation. Okay, but enough about it for now. We'll come back to it later. So let's go back to our collider, switch off use plane, go to visualizations, and we want to switch on particles, switch off collision. Okay, let's see if it looks like particles. Brilliant. So now when we play our simulation, we can see that the particles go down, as they should, and then after some time they disappear. Here we go. So you can see that here, when they exit this box, they disappear. This is the bounding box. So this is the area within which our simulation is solved. Everything outside this box is not calculated. It is a very clever, efficient way of creating simulations. So we can just ignore everything that is outside and only focus on the simulation itself. So we can adjust this box in several ways. First of all, again in the same node, I just scrolled up, we can switch on something called closed boundaries. And now when I play the simulation, instead of disappearing, our particles actually collide with the bounding box. However, we need to wait quite a long time for the particles to reach this side of the bounding box. So let's adjust the size of this bounding box. To do that, let's select Flip Solver. So click inside on this brain icon. So do not, oops, didn't want to do that. Just click once, do not display, just click once to see the parameters. And Flip Solver is the solver, the brain of our simulation. Everything is solved, calculated in here. Without it, the simulation wouldn't work. Okay, and in here we can, when you select it, we can see that we are able to adjust the bounding box. So the bounding box changed color to red, and now we can click on these walls, drag them to adjust it. If you cannot do it, make sure you have show handles displayed, selected. Adjusting the bounding box is very important. It allows you to work more efficiently. It makes your simulation more efficient. So now let's see what happens when I play it. Okay, so again, it interacts with the ground, the particles interact with the ground and also with the walls. If I go back to our first node, Flip Object, let's select it, you can see that next to closed boundaries, we have X, Y, and Z. Okay, and what do these mean? Well, we can open one of these walls by switching off one of these axes. So if we want to switch off, for example, the right wall, so let's have a look at our axis. This will be X plus, so the positive X. So if I just untick it, now we will see that the liquid will interact with all the walls apart from this one over here. In our Flip Object, we can also adjust physical properties of our liquid. So let's go to the physical tab, scroll down, and here you can see we have several physical properties such as bounce, friction, temperature, density, viscosity that we can change for our Flip fluid. Some of these, however, will not work straight away, such as viscosity. We would need to switch it on separately, but I'll do another tutorial on that. Let's now go to the next node. So we already discussed Flip Fluid from Object. We discussed Flip Solver. Now we have just Merge because we might need to have more things plugged in here. Then we have our forces, for example, gravity, and we can adjust the gravity force by adjusting these three values. So at the moment, it's very realistic because it's minus 9.8 and so on, but I can reduce it. And now you can see that the gravity force is much lower. Okay, I can also reverse gravity, so for example 9, or even change its direction. Once we're done and we want to go back to the default value, right click on where it says force and just click revert to default. And finally, our last node is the output. So we can save here our simulation as .sim to disk and then import it in another software or Houdini as well. All right, so this is our AutoDopNetwork. Let's now go back to the object level and let's see what last group we have here. And this is the network that is used for final processing of our simulation, of our geometry, of everything that is happening in the scene. So this group creates our scene ready for rendering. So we have some import, fluid compress, cache nodes where we can cache our simulation to make the rendering faster, but we also have something called particle fluid surface. So let me just display it, and now you can see that the particles are meshed. So before we had points, we had particles. Now we have an actual mesh that looks more or less like liquid, like what we will see in the render. Okay, so this is how the Flip Fluid works. It first creates the particles and then in the final step it meshes them so that we can see the actual surface of their liquid. Let's now make sure that the display flag, the blue flag, is on this node over here, dop import, and the purple flag is on the render. And let's go back to our object level. One more thing that I didn't show you in AutoDopNetwork, so let's dive in. is something called timescale. So in our flip solver, we have a lot of different options. We can adjust quality here. We can change how the particles behave and how the whole liquid behaves. We can add more parameters here, such as viscosity, density, and so on and so forth. But the one that we can use now is called timescale. And timescale allows us to control how fast or slow the simulation is happening. So we can slow down the simulation to create slow motion or speed it up. You can use that, for example, for large simulations. If you want to create waterfall, it will seem to move much slower than, for example, tap water. So if I decrease that value to, for example, half and play it, now we'll have half of the initial original speed of our simulation. So it will appear much slower. Okay, if I increase that value, however, it will be 3 times quicker than the original. All right, and again, let's right-click on timescale and revert to defaults. And we can save our scene, Ctrl S. Okay, so now let's have a look at our second tool, which is called Emit Particle Fluid. And for this one, when you hover over, you will see that it emits fluid into a flip simulation. And again, we'll need a geometry that the particles will be emitted from. So let's go back to the object level again. And next to our pick geometry, I'll drop down another geometry network. This time, I'll rename this one to Emitter Geo. Let's dive inside, and in here, I just want to create a simple sphere. So for simulations, emitter and the quality of the emitter, the shape of the emitter also is very important, because the whole simulation will take the shape of the emitter. This is our initial state. So instead of using a simple sphere, we'll add some more noise to it. First of all, let's change the primitive type to polygon mesh, because that's what we need for the simulation. And now we'll drop down a mountain node. Make sure to display it. And now I can increase the height and the element size, so I can just distort our geometry slightly, and I can see that the quality of the geometry is a bit too low, so I'll go back to the sphere and increase the number of rows and columns. Go back to the mountain node. Okay, that's a bit better. All right, so this is our emitter. So now I want a transform node so that I can move it up, display it. Again, you can use either the values or you can move it using the handles, and I'll put it on top of the pick head and move it slightly. Oh, I don't want to rotate it, so I'll just use the values. I'll move it slightly to the left just for now. And now I want to create null just to finish my network. Display the null, rename it to AutoDopNetwork. All right, so the sphere, the mountain node, the transform, and the emitter null. Let's go back to the object level. And now again, I deselect everything, click on the gray background, and now click on Emit Particle Fluid. So the first step is to select object to emit fluid from. So this is our emitter geometry. So let's select it in here and press enter. And now the second step is select a fluid object to emit into, if any. So we have another fluid simulation. So we can combine these two simulations by selecting our second simulation. And you'll see that when I select it in the viewport, when I select it here, it will take me straight to the flip object. Okay, so I select it in the viewport and press enter again. And now you'll see what happens in our AutoDopNetwork. So we have our initial original pick head, so fluid object, but we also have something called source surface from emitter geometry. And this is, or the original name of the node, volume source. This node uses the information from our geometry and then uses it to emit particles from it. And you can even see it here that the subpath leads to our object, emitter geometry, out surface. Okay, but we did not create anything like out surface, so let's see what happened here. Let's click on this icon here so that we can jump to our network, and we are definitely in the emitter geometry network. We have our sphere, the mountain node, the transform, and the null, but now we have several other nodes in here. So let me zoom in so that we can see the sphere. And now you can see that the sphere is made out of boxes. These boxes are called voxels. So these are 3D pixels. So our sphere, our emitter, is now turned to volume. So these voxels. If I switch on display create surface, and in here we have something called voxel size. So this is similar to particle separation. The lower the voxel size, the more quality we have here, the more details we will see. However, you can see that it's green, which means we cannot change this value. It's linked to somewhere else or is keyframe. So let me just expand that and click on where it says voxel size to see its path. Okay, so you can see that it multiplies something in AutoDopNetwork and something else in AutoDopNetwork. So these two are multiplied. So the first is particle separation, and the second thing is grid scale. So again, you can see that FluidInterior combines particles and volumes. So the voxel size is determined, so the quality of the emitter is determined by these two values, particle separation and grid scale, which we can adjust in our AutoDopNetwork. So right here in our flip object, so particle separation and grid scale. All right, let me go back to our emitter. So this will change automatically when you change either particle separation or grid scale, but you can also adjust this value manually if you want to. You just right click on where it says voxel and delete channels, and now you're able to adjust this value manually. And you will see that when I increase this value, we have less voxels, so lower quality. If I decrease this value, we'll have more voxels, so smoother emitter, more quality. But let me just revert that to defaults, actually undo that so that we have our link in here. Brilliant. And remember to change the display flag back to out surface, and let's go back to the object level again. Okay, now I want to hide the emitter geometry so that I can see the particles and zoom out and play the simulation to see what happens. Okay, so why can we not see anything happening here? Well, this is because of our bounding box. So let's go back to the AutoDopNetwork, select the flip solver, and now you can see that the bounding box is tiny. So we added another simulation here. We need to expand our bounding box. Okay, so let's expand it. And now let's play the sim again. So now you can see what the main difference between these two shelf tools is. The first one turns our geometry into flip fluid, so we do not add any more particles to our simulation over time, whereas the second tool, Emit Particle Fluid, emits particles on each and every frame, so we'll be adding more particles to our simulation. So to be fair, these two are very similar. The only difference is that this one emits something, this one just creates something on the very first frame and then doesn't add any more particles to the simulation. And when I play the simulation, you can also see that these two liquids are in the same bounding box and they also interact. So it's a nice, easy way of combining several simulations, flip simulations. So flip fluid from object and emit particle fluid. So if you want to adjust the physical properties of this emitting liquid simulation, you also do it in flip fluid object. However, if you make any changes here, it will apply it to both simulations. So if you want to have two simulations, for example, mixing liquids with different viscosity or density, you will need to use something called multiple solver. So it's a slightly different thing, but that's a topic for another tutorial. Okay guys, so that's it in part 1. Now I invite you to watch part 2, which is adding colliders. See you soon.